Okay. So what is important about our atmosphere? Well, one of the things is, what is our atmosphere? When we talked about other planets, I kind of mentioned, does this planet have an atmosphere? Does that planet have an atmosphere, etc. And it kind of came down to mass. Like, for instance, Mercury was so I almost said young. Mercury was so small, it doesn't have enough mass to really have an appreciable atmosphere. Now, the Earth has a substantial atmosphere, okay? And so it's all about gravity. And we need to kind of talk about what's in the Earth's atmosphere for things to make sense. But, of course, gas is one of the things that's in our atmosphere. We have suspended liquid particles. Okay, we said that the reason you see clouds milky white, especially if they're kind of low-level clouds, is water is a liquid. Okay, and of course we can have snow suspended in our atmosphere. We can also have aerosols, and I'll kind of say what that is. But here's a pretty picture, a photograph. It kind of reminds me of some of the photographs we see that come from the International Space Station, where I think even astronauts are struck by how delicate our Earth looks from outer space. And one of the things that's delicate about our Earth is our atmosphere. So it's not very thick, you know, and we count on it a lot. Okay, so I mean, kind of this bluish tinge. Now, granted, it's probably up a little bit beyond that, but it's very thin compared to the size of the Earth. So what's in our atmosphere? And of course, we need to kind of build up and look a little more at the whole weather phenomenon. But in order to understand weather, we kind of need to know what's in the atmosphere. So sometimes a current misconception out there is a lot of times you'll ask people what sort of gas is most abundant in the atmosphere, and they'll say oxygen, and that's not it. Okay, oxygen actually right now is about 21% of the air that we're breathing. Okay, it's mostly nitrogen. Okay, which, yeah, I think that's kind of interesting. Actually, what our atmosphere has changed over time. Early on, when our Earth was just still forming, it didn't have any oxygen in it. Okay, the oxygen actually came from plant life early on. Because one of the things we know plants are good in doing is basically they take in carbon dioxide and they spit out oxygen. That's where our oxygen came from. Is that not cool or what? So the thing about what is in our atmosphere, and I know up here at the top I said something about we have particles. Okay, we have liquid, we have suspended solid particles and suspended liquid particles. Those are collectively called aerosols. Now, actually the video talked about, do you remember something called condensation nuclei? Condensation nuclei. I think that was when we talked about clouds. I probably called them cloud condensation nuclei on my slide. He called them condensation nuclei. Cloud condensation nuclei is abbreviated CCN, cloud condensation nuclei. So that's actually their little dust. Do you remember I said when we talked about clouds that in order for you to go ahead and get water vapor to go and become a liquid, you a lot of times need this little dust particle that kind of gets the party started. Okay, that's an aerosol. Okay, that little dust particle. What is it? It's just a suspended particle in the air. If we didn't have dust particles, I don't know what our water cycle would really look like. Okay. So again, with regard to what's in the atmosphere, bless you. We said that nitrogen is the most abundant. You know, sometimes I've just heard it kind of 80-20, 80% nitrogen, 20% oxygen. But there's this other stuff, and actually argon, you know, we have a periodic table in here. Argon is, well, you can see AR over there. It's actually one of the noble gases, the rare gases. To me, it's kind of weird. It's like third in the list of most abundant. There are what we call permanent gases, and nitrogen, oxygen, and argon are permanent gases. We kind of have some other trace gases there. Okay. What permanent means is they're relatively constant. And then we have our variable gases. And here's our variable gases. So remember that our planet is awesome in that water can be a gas in the atmosphere, water can be a liquid, and actually water can be a solid, all in one planet. It's amazing. I'm just saying. okay? So the amount of water in our atmosphere actually varies from 0 to 4% amount of water vapor in the atmosphere. In lab yesterday, you guys went at how much water vapor there was in the room. I bet if you did that another day, you'd get a different amount of water vapor, okay? We all know that humidity can vary like that. Carbon dioxide, I actually have a slide we're probably not going to get to today, but carbon dioxide is a natural thing that's in our atmosphere. I mentioned that our atmosphere has changed over time. We didn't used to have oxygen. We used to have actually a lot more carbon dioxide than we have now, you know, way back when, you know, when our Earth was just kind of forming a crust. But right now, the amount of carbon dioxide in our atmosphere varies by two ways. I'll kind of show you what that looks like. Ozone, you may have heard of ozone before. Actually, there's good ozone and bad ozone. So ozone, the formula for ozone is O with it's an oxygen, actually 3 oxygen atoms. So it's called, ozone is O3. Okay, and like I said, there's good and there's bad ozone in the atmosphere. And we'll talk about where they are, I think, okay, and kind of why they're good and bad coming up. All right. So I can't remember, the video might have started out talking about blue skies. I think it talked about the white beautiful cloud against the blue background, okay? And and your book talks about this idea of why are our skies blue? And I think I might have mentioned this before. Like if you go to the moon, okay, and you're kind of in the daytime at the moon, you look at the sky and it's black. It's not blue. In order to have a nice blue sky, you need to have an atmosphere. Specifically, what's in our atmosphere, the nitrogen and oxygen, the 80-20%, what they're great at is basically taking that sunlight, okay, it's kind of shown here, taking that sunlight, and you kind of see this blue and purple being kind of thrown out, okay? So it doesn't throw them all out, but it throws a little bit of it out. And so there's particles, there's gases, I should say. Okay, so the N2 and the O2 in the atmosphere basically kick out the violet and the blue. They toss it to another molecule, who tosses it to another molecule, who tosses it to another molecule. You get the idea, that particular wavelength of color. That whole tossing is called scattering. And so that's actually why when you look up at our sky, okay, it has this kind of blue appearance. Bless you. I think that's kind of cool. It's called Rayleigh scattering. Now, there is some consequences, or what can happen, I guess I should say. I'll go back to this one and show you. Now, this is actually showing a sunrise or a sunset. I know it is because, you know, the sun appears to rise in the east. Okay, we get noon and it appears to set in the west. Okay, those are our horizons. So the thing about it is when the sun is kind of near our horizon at sunrise or sunset, the light from the sun has to go through more of the Earth's atmosphere. More of the Earth's atmosphere. So basically you get scattering on steroids. So this is how much of the Earth's atmosphere it goes through when it's low. Okay, this is how much it goes through when it's high. So we got that much scattering versus this much scattering. And I think I may have mentioned this before. I lose track of what I mentioned, but in the morning or in the evening when the sun is low on the horizon, if you look at kind of your speed limit signs, we should all look at our speed limit signs, but if you look at your speed limit sign, it like kind of glows orange. Things just glow orange or red in the mornings. They glow orange or red in the evenings. Okay, what's happening basically is that sunlight, most of it's been the shorter wavelengths have been scattered out. Okay, and we just get the kind of the reds and the oranges. I think that is so cool. So here's a figure from your textbook to kind of say the similar thing. Okay, showing you two suns. Of course, we are not. What is that Star Wars movie that has with two suns? Anyway, we do not have two suns, but it's showing you two suns there. It's showing you the high daytime sun, kind of the Rayleigh scattering, making the skies blue, and then the low sun, where the Rayleigh scattering basically removes the blues and violets and just gives you our reds. So this is basically a do-over slide. Raleigh scattering. Okay. Oops, one more. Okay, yeah, this is a good point. Like, especially at harvest time, I think harvest time's pretty much gone. But especially at harvest time, we can have some beautiful sunsets and sunrises. But if you get an extra dose of particulates, aerosols in the atmosphere, actually you can have some awesome extra scattering that goes on with that. So I guess we are going to get to it today. So one of the we looked at 3 variable gases. Water vapor is a variable gas, carbon dioxide is a variable gas, and ozone is a variable gas. So the thing about carbon dioxide, it varies in our atmosphere. It has 2 sort of variations. It has what we call seasonal variation throughout the year, and then it has a year-to-year variation. So this actually is a historic I don't know, it's a research facility. Basically, in one of the Hawaiian Islands, they have been monitoring carbon dioxide in the atmosphere since 1960. You know, and this was in the news maybe 3 years ago, this particular research facility. It's like, do we still need to monitor carbon dioxide in the atmosphere? I would say yes. But, so if you look closely at that, you can kind of see the little fluctuations, right? I'm kind of making them bigger. And those fluctuations are through the course of a year. Okay, so let's just look at, I'll make it one, this is really big. Okay, so basically we have a lot of carbon dioxide, okay, when the plants, let's see, how does this go? Now, I'll write down here, kind of jog my memory. Okay, so one of the things about plants, we'll take plants plus CO2 gives you O2, okay? That actually is what we call, or an outcome of photosynthesis. Right? Photosynthesis. Plants do their green thing. Plants plus CO2 gives you O2. So actually, this peak in CO2 means that, I'll say no plants. No plant activity. How's that? Why do we have a lot of CO2 at a certain time of the year? No plant activity. Now, it's not no plant activity, but it's minimal plant activity. Okay? Down here, this minimum right here, this where we don't have much CO2, why would you have not very much CO2? That would be lots of plant activity. Lots of plant activity. Okay? Makes sense? Now there is a lag, okay? So if you read my slides, actually we have this lots of plant activity occurs in the autumn. Okay, it's a lag. So this is actually in autumn. Okay? I know it seems like spring and summer and all that sort of thing. And then the other one is spring, just because of the lag. Okay? So you have a spring peak of CO2 and you have an autumn minimum of CO2, all related to plant activity. Is that not cool or what? So that's actually a seasonal trend. But do you also see from 1960 to 2000 and looks like 12 or so, yeah, maybe 2012, how it's been kind of going up? That's sad. That sort of year-to-year trend, okay, not within the same year, but year-to-year-to-year-to-year trend actually is related to human activity. There are other ways, but mostly human activity. And so, of course, burning fossil fuels would be our gas, our coal, that sort of thing. Burning fossil fuels is putting more carbon dioxide in the atmosphere. The other thing is we're removing plants. Deforestation, okay, you kind of lose the thing that is good at removing carbon dioxide. And so that's actually, those are two kind of working together. I didn't go there yet today, but I'm going to go ahead and click latest data. see where that takes us. I know that it was like 380 parts per million carbon dioxide in general in the atmosphere for a long time, and then when it went, it eked up, and when it hit the 400 parts per million mark, that was a sad day. That's been maybe a year ago. So let's see what we got today. Maybe. Let's try. Ooh. There it goes. The kneeling curve. Okay, yeah, I guess we're, all right, that's good. We're just under 400 parts per million. And again, you can see this is the same observatory. Okay, this actually is a couple days ago. But you can kind of see the variations here. And that's not bad. Be nice to stay under 400. But you can see it's probably not going to. It's kind of looking like the gray marks there. I'm just looking at this as you are, is probably the trend, their anticipated trend. So I don't know. Actually, this is the hourly. Oh, there we go. Oops. This actually then is the figure that we looked at, where you can see kind of the year-to-year trend. The hockey stick model, actually, let's see, I'm not going to pull it up, but what it does is basically say, do it this way. It's a figure, okay? So basically, if you go ahead and on a graph you have 1900, that's the year, 1950, etc. Down here we have 1800. And then in here we have the Industrial Revolution somewhere, where basically we started figuring out how we can power things by using fossil fuels. So basically the hockey stick diagram kind of goes like this, where the carbon, and this is the amount of CO2 along the y-axis, okay? It goes not much, not much, not much, and then it just kind of goes like that. Actually, that's not drawn to scale. It's not very good, but you get the idea. Okay, this sort of figure is the hockey stick. All right. So we do have time to talk about the warming effect of potentially CO2. So, give credit where credit is due. Are we glad that we have carbon dioxide in our atmosphere? Heck, yes. Do we need more carbon dioxide in our atmosphere? Probably not. Remember the planet Venus? Venus actually has a bunch of carbon dioxide in its atmosphere. Anytime you have carbon dioxide, actually you can have this sort of effect we call a greenhouse effect. There are other gases that give you a greenhouse effect. Actually, water vapor gives you a greenhouse effect as well. But in a greenhouse, we count on light coming through the glass panes in a greenhouse. Okay, now that visible light, remember we call that, in the cousins, we call that infrared radiation, visible light, we just call it visible light, okay? So basically visible light can come in, okay, it interacts with stuff in your greenhouse, okay, it turns into infrared radiation, and your glass traps infrared radiation. So the way greenhouse gases are like a greenhouse is that actually the gas particles, right here, where it's kind of got that blue thing, up here, an example of a gas that will actually block outgoing radiation is CO2. That's why CO2 is a greenhouse gas. Okay? Like I said, water vapor is a greenhouse gas. We have some other things that are greenhouse gases too. Oh, well, very good. Let's go ahead and do this slide, and I'll introduce you to actually come full circle a little bit with regard to the video. Remember the video said that it mentioned these terms. It mentioned the term troposphere and stratosphere. And we're talking more about this on Monday. But the troposphere is the lowest layer. And actually, as we talk about weather, you know, the whole water cycle and everything, and the layer we care most about is the troposphere. Above the troposphere is the stratosphere. Notice in the video it said that the kind of the layer that tops the troposphere is the tropopause. Okay, and actually we have a stratopause too. But the tropopause kind of actually is a lid to our weather. Okay, so we have troposphere, 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 tropopause, lid, stratosphere. So stratosphere, after the stratosphere, just to kind of get you thinking about it, we have the mesosphere. I don't have anything interesting to say about mesosphere. The meso, actually, if you have a mezzanine, you kind of have a middle layer. Meso means middle, okay? But it's not really the middle because there's 4 major layers. And then we can kind of think of it a couple different ways, but after the mesosphere, probably most commonly we call it the thermosphere. And the thermosphere basically is where we transition from into outer space, okay? And it's kind of weird to say where it gets. One of the things you may already know is the air gets thinner as you climb a mountain. So also the air gets thinner in all of these layers. So when you're clear out to the thermosphere, you're like, I don't know where it ends, you know. Maybe that atom of gas is really part of the Earth's atmosphere, or I'm going to say, no, I'm done here, okay? So it's hard to. There actually is one layer that kind of combines the upper mesosphere with the thermosphere, and that's called the ionosphere. And I went ahead and put a picture of northern lights there. Northern lights, I think I might have mentioned when we talked about the sun. Actually, when the sun is active, we have potential to get northern lights. And so that actually, the ionosphere is important in creating that effect. So we'll go ahead and stop here. I'm going to start with this slide on Monday because I'm going to actually click on that Red Bull jump from the stratosphere. So we'll start with that on Monday. Something to look forward to.